Sofia Abrunhosa has completed her integrated master's degree in engineering physics in 2018 from Instituto Superior Técnico from the University of Lisbon. She has been involved in multiple industrial collaborations for research and development of magnetoresistive devices at INESC Microsistemas e Nanotecnologias. And the most recent one, included in her PhD studies, comprises the construction of a portable magnetic-based barcode reader. And her research interests include design and integration of magnetic sensors and automated testing environments. So Sofia will give a talk on magnetic barcode readers, merging existing technologies into a new application. So Sofia, you may start.
Right, so good afternoon, everyone. I hope you can all see my presentation, can all hear me well. And thank you, Vania, for the introduction. And yes, for the past year, I've been working on magnetic barcode readers, which is what I bring to you today. Right, so I believe everyone is familiar with the concept of a barcode. We see it all the time in supermarkets to label different items that we can find. They all come in various shapes and sizes, different types of encoding, but they all have one thing in common, which is that they need to be visible for us to be able to detect them. But if we were to print this with a ferromagnetic material, for example, we would be able to read them using magnetic sensors. And at this point, the code does not need to be visible. And this could be very useful in applications where you can read through packaging, through a box or through an envelope, or you want to hide an extra security layer in an ID card, for example. But it comes with a drawback, is that we can no longer read at high distances. So we need to be reading at almost in contact, which is a bit of an inconvenience, really. There are other technologies that also solve some of these problems, which, for example, RFID tags, but they all come with a drawback that they are more expensive than a magnetic barcode. And for example, if you wanted to tag, let's say, reusable packages, you cannot microwave an RFID code. At least you can, but I don't recommend it. But you can definitely microwave a magnetic barcode, so you can use for these types of applications. Right, so this is where MagiD comes in. The idea is to really create a magnetic barcode technology that responds to these questions. So we need to be capable of reading at least some few millimeters away. We want a solution that is portable, usable by almost everyone, and hopefully we'll be able to use any type of materials or substrates so that we lower our costs as well. And this consortium is composed of 3 companies, so Inspectron, INESC, and Bogen. And altogether, we have 2 different approaches for this problem. So we have a scanning solution where you have your barcode static and you basically scan your reader across it, or you have a static solution where both the barcode and the reader are stuck in place. Me specifically, I'll be focusing on the swipe reader, which is what I've been developing. And this right here is its latest embodiment. So it has gone through a lot of iterations, but this is something that we are happy with at the moment. It's a stable configuration, and it's a lot better than some of the solutions that you can find commercially. So we can read up to 2 millimeters away, which is very good, and we can detect features or structures with sizes down to 200 microns, possibly a bit lower than that already. The question is, how did we, from this set of requirements, how did we manage to find the solution? What are the components and how do they interact with each other? And this will be the topic of this seminar. Right, so this is a schematic of an exploded view of this system. So starting from the bottom, we have the barcode, which is what we're trying to read. We have a TMR sensor, a flexible connector, a permanent magnet, a casing to hold everything together. And at the end, we have the electronics for the acquisition. So now I'm going through each of these components individually and try to define what are their properties and how they interact with each other. So starting from the bottom, obtaining a magnetic barcode is actually as simple as going to a regular laser jet printer and printing a pattern. Because luckily for us, these regular toners contain ferromagnetic particles, so we can immediately read them and get a good signal out of them. But how exactly are these magnetic properties of these particles? To answer this, we measured some on our vibrating sample magnetometer. So this is a typical curve of a ferromagnetic material, meaning that as we increase an external magnetic field, we now get an increased magnetic moment of our structure. In particular, this material is a soft ferromagnet, meaning that close to zero applied field, we also have a magnetic moment that is close to zero, meaning that if we are operating in this region with no external magnetic field, then our structure is not going to emit any magnetic field itself, so we cannot detect it with a magnetic sensor. So ideally, we would like to be working somewhere in here. So now we do have an external field, so our structure has an increased magnetization and creates a field that we can actually detect. So it comes as a conclusion that to measure this type of structures, an external magnetic field is required. There are other type of toners and ink formulations that have other properties, but for now I'm going to stick to this one for the sake of simplicity. Now, let's imagine that we are in this situation. Okay, we have a field, but what exactly does this field look like to a sensor? It's quite simple. So if you have a single structure, this is the field that the sensor is going to see, very nice bipolar signal. And you can immediately tell where the structure starts and ends by just figuring out where the minimum and maximum are. So if you have a more complex structure like a barcode, eventually what you have is a repetition of these tiny bars, and you arrive at something like this. So a superposition, sorry. A superposition a superposition of various signals. Apologies for that. Right, so now we know what type of signal we were expecting. Let's construct a sensor that can measure that. So in our case, our TMR chip, this tiny square here, is a 2 by 2 millimeter square. It contains 4 sensors inside, and the 4 sensors together occupy this total active area, so almost 300 microns squared. And so what we do is take this design and go into the clean room at INESC and produce sensors with this shape. And we actually eventually get a curve that is very nice, very linear at the center, and we can use to detect magnetic fields. So at this point, I have to make a break and acknowledge all the people that have helped in this process, because it's really a showmanship of true teamwork. And I wouldn't be able to do other things and focus other things if it weren't for these people. So thank you. I'm not going into much detail over this curve, but I do want to point out this value here, which is the sensitivity S0. We want the sensitivity to be as high as possible because this is what confers a very high output signal from the sensor. And sensitivity is basically the slope of this curve. So the steeper the curve, the higher the sensitivity. But let's step back into the realm of ideal curves for a second. When we represent the transfer curve, we are used to representing the field in the x-axis as the field along the sensing direction. But what will happen if there were other fields on top of these near our structure? Right, so if we had a field in the z direction, so perpendicular to the sensing plane, actually you see no change, at least for the values that we are considering, which is very good. But if now we put a field in the same direction as the sensitive direction, we get a shift in the curve. This is not necessarily bad because the sensitivity here is not worse for this case, but in ideal cases, when we get very close to the transition, the sensitivity lowers, so we want to avoid that. Now, if we put a field in the y direction, what we see is a broadening of the linear range of our curve, meaning that the slope now decreases a lot. So if we are targeting real applications, we want to limit as much as possible fields in these two directions. Because if we don't, I'm going to show you what happens. So we have a perfectly nice sensor transfer curve here with a good sensitivity. And if you place it around different fields without being too careful, this is what happens. So we completely lose our sensitivity just because the curve shifts a lot and loses some of its slope. It's also important to note that we also lose a bit of coercivity. So we can actually completely lose our coercivity just because of the presence of the white field. So it's a bit of a good thing when we might want to stick to having some of it. But yes, the message here is that TMR sensors are very susceptible to external magnetic fields. So we want to minimize them as much as possible to minimize the loss of sensitivity. Now we have our sensor and we want to connect it to the rest of the electronics. So at the start, we decided to go for a flexible printed circuit simply because we have very limited space in here. So you can see the chip in there on top of the FPC. We were a bit concerned about the noise level and reliability of the connection at the start, but eventually we solved all of these problems. So we started by using a process at INESC MN. So we used wet etch of a copper sheet on top of polyamide, and this worked very well. But once we were happy with the design, we eventually outsourced this just so we could have a faster development process, and also we can improve a bit of the reliability on this connection here. So this part actually has been going quite well. Right, now for the permanent magnet, this is the most critical point of all of this work, because if you remember from the start, the barcode requires an external magnetic field for it to be able to be read, but the sensor is now very sensitive to an external magnetic field. So when we choose a permanent magnet, we have to be very, very careful with the choice that we make. So our best candidates were a ring magnet and a disk magnet. And so we wanted to minimize the radial field, sorry. We wanted to minimize the radial field, X and Y directions, but we also wanted to maximize the vertical field. So we've done some simulations for that. And here we see the radial field for these two shapes. So if we place a sensor here in this red area, you're not going to see anything. So there's no point in that. What we want to do is place a sensor somewhere in these tiny areas where we're probably going to be seeing anything. But how tiny are these areas? So we established a boundary, which was we could only place sensors in a region where the field was smaller than 1 millitesla, which means for the ring magnet, this is a radius of 400 microns. But for the disk magnet, this is now 170 microns, which is very problematic because this is the size of our sensor effectively. But in regards to the vertical field, we wanted to have the maximum field as we wanted to maximize this as much as we could. But in reality, the maximum fields of each of the two shapes were identical. The only thing that is changing is the shape of this curve. So the disk has a bit of a plateau and the ring has a dip here at the center. But we were using a scanning application. So maybe we were scanning fast enough for this not to be a concern. And in most cases, it wasn't. So given this reason here, so we want to have as much space as we could for our sensor. So we chose to go with the ring magnet first. And this is what the signal looks like. So it actually looks like quite a good signal, and we could decode things very easily with it, as the sensitivity is also quite high. The only drawback was when we started to read things far away, we started to lose a lot of signal and we couldn't actually measure things very, very well. So at that point, we swapped onto the disk magnet, and although the sensitivity dropped, the amplitude of the signal is twice as high. So this was very good. Furthermore, for me to be able to read this pattern, I was reading through the back of the paper. So I was flipping the paper around and reading the barcode on the other side. Otherwise, I would saturate the amplifiers. So in truth, this amplitude is a lot higher than that. So the conclusion is, although the disk magnet has a smaller low field region, it provides a higher barcode signal, which means we can read it at higher depths. And since the disk is also smaller, we provide a more ergonomic shape for the reader. Right, Now onto the holder. It has a clear purpose of holding the components together and also giving some protection to the sensor chip, but it has two other functions. One of them is to limit the tilt of the sensor, because if the sensor is a bit tilted, we see that the shape of the signal completely changes, and that can be problematic for the decoding. Another reason is that we want to minimize the distance from the barcode to the sensor as much as possible, because if we are too far away, our amplitude obviously drops, but we also lose resolution in these smaller peaks here, which again is a problem for the decoding. So we have to choose our assembly carefully, considering all of these things. And actually, this is where we were about a year ago. This is where we started. We didn't even have a connector, so we were using a pair of probes. And this is where we are at the moment, which is looking quite good, and we're probably going to change this further. But in the meantime, we've had a lot of iterations, some looking stranger than others, but all of them trying to maximize the output signal and also the ergonomic shape of our reader. And you can clearly see the transition between the ring magnets and then eventually the disc magnets. Right, so now that we're happy with the full assembly of our sensor, it's time to connect them to the electronics, and that's where our colleagues at Inspection come in. Right, so we have an acquisition PCB where it has filters, amplifiers, processing unit, etc. This then connects to the PC application, and from there we can retrieve our signal. And also, it also allows us to decode the information contained in this signal and tell us, yes, you're reading a barcode that corresponds to 14F70. Right, so we were happy with this configuration, but now we wanted to do the things in a bit manner more controlled. Right, so we constructed a test bench, which is basically the structure of a 3D printer adapted to our necessities. And the idea here is that we can do automated and controlled scans in here. So instead of scanning by hand, which happens to be convenient, it's not very precise. So if you want to really compare different configurations or try different speeds of reading, etc., we want to do this here. Also, since the position of the sensor inside that tiny region of the magnet is very critical, it's also helpful to do this here when in a more controlled environment instead of doing it by hand. So we also can do this here. Right, so in this slide, you can see the scanning configuration. So basically we have a structure that sticks our swipe reader to this carriage. It's then connected to this PC application, and now we can tell our table to move in this direction to perform scans. But now for the alignment part. As I just said, this magnet provides a very limited region where we can place our sensor. So it requires a very good accuracy from this procedure. So let's imagine our sensor in a void, so without any external magnetic fields being applied except for the one that we are interested in. The curve looks very nice with a good sensitivity, but if we now place a magnet in here without being too careful, this is what happens. So magnet is completely deviated from the sensor, which means that we have a huge loss in sensitivity. But if we are more careful, and this is an actual result with the new setup, we can actually align the magnet a lot better, which means that we don't lose as much sensitivity. So this is the target of that we're trying to achieve. We are considering like a drop of, or a final sensitivity of 70% of the initial value to be a good achievement. Right, so how is this actually done? So we have a completely different configuration. So instead of having a support for the swipe reader, we have a support for the FPC and the chip in there. We also have a support for the disc magnet, like you see here, and the FPC plus the TMR chip is free to move around the disc magnet to find the optimal position. But the most critical part of this setup are these two Helmholtz coils. And what are they doing here exactly? So if we are trying to maximize our sensitivity, it only makes sense that when aligning the sensor, we measure it. So these two coils are driven with an AC current, and they in turn create an AC magnetic field. when the sensor is placed in there, in this AC magnetic field, it is also going to output an AC voltage. And if we place a misaligned sensor in here, this voltage is going to be smaller because it depends on the sensitivity. But if we have good alignment, then this amplitude is going to be larger. So this is what we're trying to achieve. The better this alignment, the higher the sensitivity, therefore the higher the amplitude. So we want to find the point where the amplitude is maximum. And how do we do that? So we initially place our sensor in a position that visually looks like a good position, for example, in this center here, and then we ask it to define a matrix around this point and measure the sensitivity at each of those points. And it actually tells us, well, you missed, the center is actually here. And okay, we tell it to move to that center and draw a new matrix around it and confirm that we have found the point with maximum sensitivity. But now we have more precision than this. So what we do next is divide this square into a new matrix of its own. So we go into here, we define a new matrix and ask it to measure the amplitude again. It actually tells us, well, yeah, the maximum amplitude is here at this corner. So it will correspond to a corner here. So we do the same thing again, define a new matrix around that and measure it until we find the most optimal point. And when we end at minimum range, that minimum precision that we can have, which is about 50 microns, we say that this is the point of highest sensitivity, and then we can glue our sensor. So this has a few advantages over doing an optical alignment. One is that, well, obviously we are measuring sensitivity directly. We are not concerned of magnet non-uniformity. So for example, if the geometric sensor of the magnet is not exactly its magnetic sensor, well, we don't care about that. And it's also independent of the alignment between the sensor and the FPC. So we bypass that completely because we are aligning the sensor with the magnet. Right, so, and for future work, some of the things we're going to do are to refine this alignment procedure because there's still bits in automation and the algorithm itself that can be improved. On top of that, we are exploring an electromagnet approach. So instead of using a permanent magnet, we'll be using a coil. And we are actually in the process of patenting this implementation. On top of that, I'll probably be doing some bits of acquisition and decoding in the next few months as well, just to complement some of the work that we have been doing. And although this looks like a reasonable plan, like all scientific projects and engineering projects we all have open questions that we would like to go back and answer. And here's a list of them. And also, if you don't have any questions for the discussion, aren't feeling too creative, I can come back to this slide. Right, so I'm finishing up. And before finishing up, I would like to thank my supervisor and co-supervisor for the support being given during my PhD. I want to thank the team at Inspectron because it has been an absolute pleasure to work with them. And last but not least, I want to thank my colleagues at INESC MN because in science and engineering, nobody works alone and we all rely on each other. So thank you, and thank you for watching. I hope I've been able to teach you something new.
Very, very good presentation, Sofia. Thank you for sharing your extensive work. I see. So does anyone have a question for Sofia? You can raise your hand or just pose your question. If not, I will start. So Sofia, you say that you are reading the signal that is emitted by the magnetic ink that is defined on your paper, right? So have you determined the minimum concentration of magnetic content that to be able to detect the field that is generated?
Actually, we have not gone too much into that. So we've only tried a few inks that were few formulations that are already available. So we've tried a few tunnel formulations. There is one type of ink that is very used for character recognition in Czech. So it's called MICR ink. Yes, but other than that, we've not gone too deep into that.
But that is perfect. You are already using commercial links, and
yes, it's very convenient, really.
Giving very good results. Oh, great.
Yes.
So Ian is posing a question, and also Emery has his hand raised. So Ian says, aside from the technical content, the slides are superb. It's not a question, it's a praise. Natalie also says that this is the best physics presentation she's ever seen, which is very good. And Emrys, you want to pose your question? Go ahead.
Yes, great presentation, Sofia. Thank you very much. The process of automating alignment of the chip on the magnet. You mentioned that you're limited by the positioning resolution of the printer assembly. And I see that you've still got quite significant, if those numbers are actually real, you've still got quite significant gradient around the critical point there. Can you get any more sensitivity by reducing that resolution? Is that possible?
I've tried. The minimum I've tried was about 25 microns, or steps of 25 microns, and at that point it was very hard to pinpoint what exactly was the most sensitive point. So I had about 3 or 4 points that were almost all the same, and the algorithm was hopping between all 3. So I was considering that to be the limit of our resolution, 25 microns.
Okay, thank you.
Another question from the audience? So actually that we are in this slide, what is the size of these squares in the matrix that you are using?
Yeah, sorry, the units are in millimeters, so the distance between these two squares is 100 microns.
Okay.
Which is, well, a lot better than what we can do by hand, so there's no question in that.
And you have the sensor facing the magnet exactly planar.
Yes, it will be as close as it would be when it was glued finally. So I do this alignment, so the sensor moves around, and then when I find the exact position, I raise the sensor, put some glue on the magnet, and then lower it back to the initial position.
And this amount of glue, is it controlled?
No, I do it with a paintbrush, but it's not a problem.
But it's a very thin layer.
Yes, and it glues very fast, 5 seconds, and then I cannot move it anymore.
Okay. Can you discuss a bit on the materials that you are using for the sensor?
Sure. Right, so this is a regular TMR sensor. What we're actually most interested in is these 2 layers, which we consider to be the free layer. So when we apply a magnetic field in this direction, our free layer is going to point in this direction, and when it changes, the free layer is going to change with it. But then we have other layers that what we do basically is improve the linearity of this slope here. So if we only had that layer plus another, that ferromagnetic layer plus another, this one here, we see is the square curve. And what we want is a linear curve so that we are able to correlate a magnetic field with the resistance. So we need all of these accessories to be able to do that. I don't know how much detail you want from this, but
Ian, go ahead.
I've got a question about the overall limits of this. So we've achieved a TMR of 128% or this sensitivity. How far can you go with that?
For this particular arrangement of stack, we usually see, let's say, 180 up to 200% is not too difficult to achieve. If we want to go to a higher sensitivity than that, which means reducing the linear range that you see here, so effectively increasing your sensitivity even more, we need another few layers to provide a higher sensitivity on that. And so once we achieve that with this layer, with this type of construction, we can, it's a logical step to go and try that as well.
Excellent, we can discuss it.
Yes.
No, that's great, thank you.
Sofia, Timur is your co-advisor, right?
Yes.
Timur, do you want to comment on Sofia's work? Not sure that we still have Timur. Okay, Sofia, can we go to slide 20 and check some of your very nice questions? Actually, you showed a very nice photograph with all the versions of your how do you say that?
Reader,
your assembly. So I'm seeing that you are using different materials. Have you considered the influence of the material on your, like, do you think there will be any interference? Because you have something in, I think, aluminium, but then you pass on to some plastic. Yeah,
so this is acrylic. This is aluminium, this too. And then after here, it's 3D printed material. So this is PLA and these two are nylon. And yes, I considered that as soon as we were trying new configurations, I would take an older one and pass through the new holder just to see if we got any magnetic signal from that. And the answer is no. So the assembled material is not affecting the signal that we're getting out of the sensor.
So Timur says he's having some problems with the microphone, so he's not able to speak.
Yes, that's fine.
So let's go to your slide 20 and discuss a bit on the issues you are like thinking about.
Yeah, so the first question is it worth going back and explore other magnets again? So our problem at the start was, well, we have a very limited region where we can place our sensor, but now we have a very good way of placing it. So does it open up new possibilities with other configurations that we discarded initially or not? So we have to consider that.
And do you think other shapes will be more interesting instead of, because
there's one I still have in the back of my mind. A square, I don't like a square too much because we have a lot of square fields.
The area where your sensors are is more or less of, no, it's a rectangular area, right? 150 by 2 something.
Yes, yes. No, the other shape I still haven't tried is a cone. So instead of having a disc with a fixed diameter, we'll do something like this. So we can still conserve a tip shape with what you're targeting, but we get more magnetic material. So this could increase our signal even further. That's an example.
And then you mentioned extreme conditions. So your application would be for?
It's going to be this one in particular. So portable reader, I don't think it's going to be inside very large temperatures.
Usually reading barcodes or some information on, for example, bills, something like that, right? So
yes, exactly. So I don't think
that are small, that are usually flexible and that are accessible to everyone.
But I don't think that in this particular embodiment, it would be a problem. But for example, if you had an industrial application, a sensor, I see a lot of people in there, a sensor placed in an industrial environment, yes, maybe you could have very high temperatures.
But then you'd have to also think about all the encapsulation of the sensor, right?
Exactly. So PLA, the flexible connector, all of it is not very good at resisting high temperatures.
Go ahead, Sara, which is Pedro and João and Pedro Ribeiro and Jorge, and I'm not seeing Tiago Coutinho, so a lot of people inside the room.
The question is, why are you thinking of using the electromagnet approach? What advantages do you expect over using just the permanent magnet?
Right, so the advantage of the electromagnet is that you can turn it on and off. So technically you could turn it on to increase magnetization of the ink and then turn it off to do the measurement. So if you do this very fast, you can do this while you're scanning and you won't have an effect on the sensitivity in theory.
But if you have an electromagnet, it would probably be small, right? Around
yes, a small electromagnet, which means a small magnetic field that reaches barcode, then a small signal coming from the barcode itself. So but yes, we will be working, yes.
But also you are applying current into coils. So you'll have additional issues, for example, thermal issues.
Exactly, yes.
So, but that's a nice point.
Any other questions? Just trying to figure out.
Go ahead, go ahead.
Me? I'm not sure if anyone is asked. Okay. No, I was just saying that it's really a matter of figuring out which one performs best in which conditions. So with your electromagnet, we're targeting small signals, but if we can actually measure them, maybe that's a better approach.
And in this case, would you position the electromagnet below or above the sensor?
So let me point, the sensor will be here. So the sensor is close to the barcode and then the electromagnet on the back of the sensor.
So one additional issue you also have is you need to provide energy to the system.
Yes.
And with a permanent magnet, you have like no energy. No
yes, and it's also a portable system, which is battery operated. So we have to be careful with how much current we put in that.
Anyone with a question to Sofia? Everyone is really, really shy today. So let's continue on with your very nice list of we feel that you take a lot of time thinking on where you are and where you want to go. So,
yes, this list was larger, but someone complained the slide had too much text. Yeah. Yeah. So for example, this one. So we have, with a permanent magnet, we have a lot of crossed fields and we are always trying to mitigate this. But is it possible to do some sort of shielding on the sensor itself? So there are some techniques that we use to concentrate fields, but we could also use them to dissipate fields, for example. So there's something called magnetic flux guides that we sometimes make in our sensors. So this could be useful in guiding the fields away from the center of the sensor, for example. And we haven't tried that yet because it's very complex, or it's added steps on top of an already complex process.
And don't you think that would affect the signal that you are trying to read?
We have to be very careful with that, yes. But there are simulations that we can do, find a configuration that minimizes the external fields, but also doesn't decrease too much the target field.
Part of the scalability of the alignment protocol, I think it would be more or less straightforward now.
Yes, I mean, it's completely automated for now. And actually, I've made it so that this part and this part are removable. So technically, we could have a lot of these parts in stock and just change them as we go along.
Yes, and if you get more motors that have higher resolution, then you can go into even.
Yes, the only drawback at the moment is that this process takes about 20 minutes. So it's not very feasible if you were making 1,000 of these. But if we can lower that, or we have replications of the system, then yes, maybe we could target that.
Do you think in this case AI could assist in this positioning? Because
yes, definitely.
It could learn from, okay, I'm closer, I'm getting closer, so I'm not going for the whole region that was initially foreseen.
There are lots of algorithms that can be used here. I used the matrix first because it was the simple one really to get working. Emrys had an idea, which was to use the algorithm they use to guide missiles. So basically, you have a circle that is going along and trying to find the optimal point. So I want to try that one, even if it doesn't work. But yes. And definitely, yes, there are these, let's say, discrete algorithms, but then we can move forward to artificial intelligence and play a bit with that.
Nice. So can we return to anyone has a question for Sofia? Just go ahead and pose your question. Don't be shy. Can we return to the list?
Sure.
There's a very good question in the chat.
Oh, sorry. Oh, my chat is not. Oh, okay. Okay. It was hidden. So Fabien is asking what is the advantage over MICR readers used by the US banks to read checks?
Yes, so these readers use something called inductive heads, which is something that has been used a lot in magnetic detection technology. But the advantage of TMR sensors is that they are incredibly sensitive compared to that. So we can measure much smaller signals than they can measure with these MICR readers. So it's really the next evolution step in this technology.
Fabien, was that clear for you? Ah, very welcome. Any other question from the audience? So let's continue. So an analytical model. Okay. Do you wanna?
Yes, so okay,
What you mean?
comment on this. This is something I've been wanting to do for a long time, but I haven't actually done, I haven't been able to justify actually doing it. So this knowledge that we have here, and it's the base for our choice of magnet, etc. This is very empirical knowledge. So we don't have, there are some, there's an analytical background behind this, but I would like to have a model that exactly describes this. And this could be as simple as taking what we call the energy balance equation for the sensor and putting there, instead of just an HX field, which is what we usually do, I would put a field in all three configurations, and could probably, instead of being drawings, I could probably predict this behavior just using that model. I just haven't been doing that because it takes too long.
So do you have an idea of how long could it take to develop such a model? For like months, years?
No, I'd say a month, really. But it's a month that I don't have at the moment.
Yeah, time is short. And you still had one last comment on your last slide?
Oh, yes. This is actually a question that I'm going to answer in a few months. It's similar to what you asked a bit ago. So instead of using discrete algorithms to decode our signal, could it be useful to teach a machine on how to decode them? So I'm probably going to do this by the end of my PhD. Is something that I'd like to try.
Okay, so the audience has any other question or comment for that matter? No? So I would like to thank Sofia for this very, very nice discussion on her work and on the usage of magnetoresistive sensors and how to engineer solutions to implement those sensors in tight spaces and complex structures.